It's the Summer of Math Exposition 2023. So let's talk about the forgotten digit-by-digit algorithms. In the mid-1950s, early computer scientists were developing some of the first math libraries for the new stored program computers. Among their experimental subroutines was a class of binary digit-by-digit algorithms for calculating certain inverse functions using simple iterations and no stored constants. Here's one such algorithm which calculates a transcendental function, the arccosine, one binary digit at a time, using no constants other than 1 and 2. So how does this work? Can it be extended to other functions? Can it be reversed to calculate cosine? What insights can this class of digit-by-digit algorithms give us into the functions they calculate? Though it has a unique simplicity, researchers noted that this algorithm loses accuracy for some inputs and that its convergence is simply linear. Thus, it was soon abandoned and largely forgotten with time. Can we take a new look at overcoming its shortcomings? Put simply, those algorithms work by using induction to minimize an error value at each iteration. We'll examine two such error formulas, do some examples, and finally reverse the arccosine to create a new algorithm for cosine. Here are two different error formulas which can be expressed as inductive recurrence relations. It's not obvious at first, but each has a key quality which makes it surprisingly easy to calculate when certain conditions are met. Let's take a look at each of these error formulas and how they work, and try some examples. Here's error formula number 1. It's some function f of that purple part in the middle, which we're calling epsilon. But here's the key quality to this formula. We never actually have to calculate that purple part, epsilon. Instead, we calculate e inductively at each step. I'll show you what I mean. So x, our output value, starts out at 0, and e, the error value, starts out with that formula, I replaced with 0. Simplifying, and the initial value for e is in fact the input value. How simple is that? Let's build inductive recurrence relations for x, the output, and e, the error value. Here we define two new functions. g1 is how we translate f of x to f of 2x. g2 is how we translate f of x to f of 2x minus some constant a. Case 1 is where x doesn't change. Case 2 is where we add a single 1 bit to x. Now let's figure out the error value for case 1. Here x doesn't change, so we replace x sub I plus 1 with x sub I. And there's our purple epsilon, which we never compute. But that f of 2 times epsilon is g1 of f of epsilon, which is g1 of e, and that's a good simplification. Now let's figure out the error value for case 2, when we add a 1 bit to x. So we make that substitution for x sub I plus 1, do some algebra, and there's f of 2 times epsilon minus a, which is g2 of e. Now we have recurrence relations for x and e, but how do we choose between case 1 and case 2? What's the inflection point for when to add that 1 bit to x? The goal is to add the 1 bit in red without the inner epsilon value crossing 0. Simplifying, that's case 2, when epsilon is greater than or equal to half of a. Except that we don't actually calculate epsilon. So we apply the function f, and the inflection point is when the error value e is greater than or equal to the constant f of a over 2. If f is a decreasing function, then we reverse that inequality. So now we have the recurrence relations for x and e. We know the inflection point for case 1 versus case 2, but we still haven't chosen the constant a. There are 4 considerations. First, f of ax is monotonic, meaning it only increases or decreases as x goes from 0 to 1. F of a over 2 is a convenient constant for comparison as our inflection point. Given f of x, we can easily compute f of 2x minus a, which is our g2 function, and our input value y can range from f of 0 to f of a. So let's use error formula number 1 to generate an algorithm to calculate the logarithm. Here, our f of x will be 2 to the x, so the inverse will be the logarithm base 2, and we'll calculate the log base 2 divided by a. We'll choose a equals 2. F of ax is monotonic everywhere. F of a over 2 equals 2, a convenient constant for comparison. F of 2x minus a, our g2 function, is f squared of x divided by 2 squared. And the input y can range from 1 to 4. Here's the standard recurrence for x, the output value. And we've specified cases 1 and 2. And we add the recurrence relations for the error value e with its two translation functions g1 and g2. F of 2x equals f squared of x, so for g1 we square its argument. F of 2x minus a is f squared of x divided by 2 to the a, so for g2 we square and divide by 2 squared. And that is our algorithm for the logarithm. We start with the error value e equals the input value y, and x equals 0. At each iteration, we magnify e by squaring it. When e on the vertical axis goes above the inflection point 2, we add a 1 bit to the output x. Now let's use error formula number 1 to generate another algorithm, the arccosine. We set up the standard recurrence relations for the output x and error value e, then choose a equals pi. F of pi x decreases as x goes from 0 to 1. Therefore, we reverse the inequalities for cases 1 and 2. F of pi over 2 equals 0, a convenient inflection point for the two cases. And f of 2x minus pi equals minus f of 2x, and therefore our g2 function is simply minus g1. So now we specify the g1 and g2 functions. The cosine double angle identity says that cosine of 2x equals 2 cosine squared of x minus 1. So that's our g1 function. Take its argument, square it, double it, and subtract 1. And we already know that the g2 function is the opposite of g1. So make that replacement, and this is the arccosine algorithm. In fact, this is that arccosine algorithm from the beginning of the presentation. We start with the error value e equals the input value y. At each iteration, we magnify e by square, double, and subtract 1. When e goes below 0, the inflection point, we add a 1 bit to the output x. Now let's take a look at our alternate algorithm builder with error formula number 2. Again, we have output value x, error value e, and now we also have a helper value d. Let's derive the initial values. X starts at 0. For e, we replace I with 0 and simplify down to e sub 0 is the input value y minus a constant f of 0. Again, convenient. Now it turns out that the recurrence relation for e is always the same here. For case 1, we double it. For case 2, we double its difference from d. If the function f decreases, then we reverse the inequality. Now let's deal with the helper value d. To initialize, we set I equals 0 and simplify. And yet again, we get a convenient constant. What about calculating d in general? Well, here's the key. The expression for d can be simplified only once the function f of x is specified. So let's do that using error formula number 2 to generate an algorithm for the square root. So here we specify our f of x is x squared. That will let us calculate the inverse, square root of y, divided by the constant a. And we choose a equals 16 because it'll be convenient later on. So the function f is monotonic everywhere. We have 64, our initialization value, and the input y can range from f of 0 to f of a, or 0 to 256. Now we build our recurrence relation for x and specify case 1 and case 2. Likewise, for the error value e and the helper value d, now that we've specified f of x, we can simplify the expression for d. Now replace a with 16 and simplify the formula for d. The x squared terms drop out, and we end up with power of 2 times x plus a power of 2. D can also be expressed as a recurrence relation if it helps. And there it is. Now, you may have seen this algorithm before. This is, in fact, the binary form of the longhand square root method. So there on the right, we're going to do the longhand square root of 169, but in binary. The table on the left will have the algorithmic values and also those same values scaled by a factor of 2, which will be the same values that we're getting on the right. So the way that the longhand binary square root works is that you use 2 bits at a time from the radicand, 169. Then you take the current partial result, which is currently empty, append a 0, 1, and subtract. The result of the subtraction is non-negative, so put a 1 in the result and bring down the next 2 bits from the radicand, giving 1, 1, 0. Then take the current partial result 1, append 0, 1, and subtract. The result of that subtraction is non-negative, so put a 1 in the result, bring down the next 1, 0, giving 1, 1, 0. Then take the current partial result, 1, 1, append 0, 1, and subtract. The result is negative, so discard that and put a 0 in the result. Bring down the 1, 1, 0, plus the next 2 bits, 0, 1. Again, take the current partial result, 1, 1, 0, append 0, 1, and subtract. Since the value is non-negative, we put another 1 in the result, and that's our answer. The square root of 169 is 13. If the remainder weren't 0, we could put down a decimal point, or a binary point, and continue with the iterations as far as we want. There are 2 important things to note here. For 8 bits input, we got 4 bits of output. In general, for every 2n bits of input, we'll generate n bits of output. Also, this algorithm generates a true remainder, the scaled value of e. At every step, the radicand y, 169 here, is equal to the square of the result plus the remainder r. So as r goes to 0, 16x goes to the square root of y. That remainder carries extra information, which we can use to extend the accuracy of the algorithm. Now, let's go back and revisit that arccosine algorithm. Then we'll reverse it. Here it is again, the arccosine algorithm, using error formula number 1. Now, here's an equivalent arccosine algorithm, simplified even more. At each step, we'll choose the next binary digit of x according to that formula for the b bits. Notice that since we're going to reverse this algorithm, doing the inverse of that e calculation will involve add 1, divide by 2, square root. And here's how we'll do it. Given a binary number between 0 and 1, we will recode it by doing bitwise exclusive OR on adjacent bits. 0 gives a +1, 1 gives a -1. Then we generate the y values by iterating from n down to 0, which gives us the cosine of pi times the input x of n. And that is the exact algebraic representation. It's not an approximation, algebraically. So let's do an example of calculating the cosine using our new algorithm. Here we'll see that given an angle as a fractional power of 2 in binary, we can derive the exact algebraic representation of its cosine, almost by inspection. Here our input will be 11/32, which in binary is 0.01011. We're going to recode that input. We take the bits, do the exclusive OR transformation of adjacent bits, giving us plus, minus, 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 plus, minus. We apply that to the recurrence for y as I goes from 5 down to 0, generating this square root tower. And that is the exact algebraic representation of the cosine of 11 pi over 32. In tabular form, we can see what's happening. We're taking the cosine of various angles, like stepping stones, until we get to the angle of interest. But question, what if the angle of interest isn't a fractional power of 2? We go into great detail on how to do that and more in the accompanying paper. Link in the notes. Finally, let's talk about the implementation accuracy of this algorithm and its inverse, the original arccosine. From 1957, the method for computing certain inverse functions one binary digit at a time, which was described by D.R. Morrison, has been used in this laboratory. The method gives poor accuracy for certain values of the argument. The number of correct figures in the value obtained for an inverse cosine or similar function may be only about half as many as Morrison suggests. Historical note: Donald R. Morrison was a computer scientist at the Sandia National Laboratories in New Mexico. Morris V. Wilks and David J. Wheeler were computer scientists at the University of Cambridge Mathematical Laboratory working on the EDSAC computer. Sir Maurice Wilks was eventually knighted in the year 2000. So let's consider what happens when you implement this cosine algorithm in hardware or software. This is the essence of the cosine algorithm. Now, when you get many plus ones in a row for the s values, then yes, y rapidly converges to 1, and extra bits of precision are pushed off the end of the register. But are the precision bits really lost? Here's a very rough diagram of how we calculate the cosine. Remember the square root algorithm, how it takes 2n bits of input and produces n bits of output? And then we feed those n bits of output back into the input as 2n bits. How do n bits become 2n bits? Do we simply append zeros? If we do, then that is at the source of how this algorithm can be inaccurate. Let's think about how our square root algorithm works with the remainder. We have the output value, x squared, plus the remainder equals z. Now, we most care about accuracy as z and x go to 1. So we can more accurately represent the square root of z as x plus 1/2 of r. Why is that? Well, you're familiar with the rule that if you take the square root of 1 plus some small value epsilon, that can be approximated as 1 plus half of epsilon. So in that way, the needed extra bits of accuracy are immediately available in the remainder register when we need it most. These algorithms to calculate square root, cosine, and sine have been implemented in hardware using just 5 shift registers, a subtractor, and some other logic gates. No ROMs, no stored constants were used. As far as the accuracy, the cosine error is less than 1.3 in 2 to the 16. This video has been an overview of digit-by-digit algorithms, how to generate them, and their implications for trigonometric functions. Find a deep dive in the accompanying paper at math.fowlksfamily.com/theforgottenalgorithms.pdf. Find hardware implementation details at math.fowlksfamily.com. I'd be interested to hear your thoughts. What other functions can you calculate digit by digit?